this video, we'll talk about derivative and integration techniques. In Calculus 1, after about a month or so, you'll start getting into what a derivative is and how to, and the various methods and techniques on how to take derivatives of certain functions. Once you learn all the methods on how to take the derivative of all the functions, then they introduce integration, which, as I've mentioned before, integration is a much more useful and valuable math tool. And it's simply the act of taking an antiderivative, which is basically, as it sounds, doing the opposite of the derivative technique that you were taught previously. So with that, we'll review the important differentiation techniques, and then we'll go over how they relate to the integral and how we take the antiderivative. And then we'll talk about some of the more important integration techniques like U substitution and trig substitution. So in the beginning, you'll actually learn the limit definition of a derivative, because as we were discussing, your first month and a half of calculus or so would have been devoted towards learning how to evaluate or how to read limits and take the properties from limit graphs. After you get comfortable taking limits, then they introduce the limit definition of a derivative, which looks something like this. Or minus, sorry. Or actually, it's not f of delta x, it's just delta x. So basically, the limit definition of a derivative is, as I've said before, a derivative is the instantaneous rate of change. So you take a limit as some function or some value delta x approaches zero. Again, approaches zero. So it's not exactly zero, but it's approaching zero. Basically, it's a mathematical way of saying that this is an infinitesimally small change. So it's a change, but it's not a change that you would be able to visibly see, or that you would be able to see on a larger scale. So right here, we have the original function plus some small change. So you're at this value, at some value, you're doing a small change. Then you're subtracting it by the original functional value and then dividing it by the small change. And then you would have to do certain techniques on how to get the denominator not being zero, so that you can evaluate this limit and then get a value, and whatever your value is would be the derivative of that function at whatever point they give you. So that's the limit definition of a derivative, but that is only a short time span in your learning before they actually introduce you all of these important techniques, and then you can take derivatives much simpler and quicker without having to go through much of the hassle. So right here with the power rule, this one we can do a quick example of. So this says if you're taking the derivative of some function x raised to some number, then the derivative is that number brought down in front of the original thing with the exponent -1. So all that looks like is that if I have a function f of x is equal to x to the 6th, then my derivative f prime of x is equal to 6, because I bring the exponent down in front, 6x, and then I have raised to the 5th because I have the original exponent n -1. So the original exponent subtracted by 1. All right, simple enough. that technique is honestly used a lot of times while using the other techniques. So for instance, like if we're doing product rule is a way to take a derivative when you have two functions of x multiplied by each other. What that means is if I have something like, all right, here, side note, here, let me set up the function. Let me set up the question, and then I'll give you another piece of information. If I have something like 2x e to the x, right here is an exponential. There is a rule with exponentials that aren't dictated here that I'll explain now. Basically, if I have a function which is just equal to an exponential, when I take the derivative of that function, you're technically doing a modification of chain rule. So it is chain rule, which we'll get into here, where you are taking the exponent, bringing it down in front, and doing all this yada, yada, yada. However, for when you're working with an exponential, that first initial derivative that you take is actually the original e to the x function. So if this is e to the 2x, I take the derivative of it, where this is like the usual derivative of it for everything else. So for everything else, that's how you would do it. But for an exponential, you take the derivative and be like, okay, it stays the same. So it's e to the 2x. But now you do the chain rule portion where you're multiplying it by the derivative of the inside function. This right here is the inside function. Like this is the g of x part. This is why you're not bringing it down as an exponent, because this 2x isn't really an exponent. It's not an exponent. It's like this g of x function. It's like the inside function. So if I'm multiplying by the derivative of that, the derivative of 2x is just equal to 2. So my answer is 2e to the 2x for that function when I take a derivative. Okay, so now if I am taking the derivative of something like 2x e to the x, hell, let's just make this 2x e to the 2x. These are two separate functions of x. You have 2x multiplied by e to the 2x, which is synonymous with having one function of x times another function of x. Whenever you take the derivative of a function that has two functions of x, then you take the derivative of the first one multiplied by the original second one, and you add it by the original first one multiplied by the derivative of the second one. What that looks like is if I take the derivative of this function, I'm taking the derivative of the first thing. So 2x is the first thing, and I know the derivative of 2x is just 2. So I have 2e to the 2x for my first thing right here. Plus, I keep the first part the same. So now I have 2x. But now I'm taking the derivative of e to the 2x. And I know the derivative of e to the 2x over here looks like 2e to the 2x. So it looks like 2e to the 2x. So right here then would be my derivative of this function. All right, so that's product rule. Chain rule, we already kind of peeked at a little bit here, but it goes like something like this. So if you have a nested function of x, and a nested function is something where you have like a function inside of a function. Ergo, like if you have an exponential right here, your outside function is e, the exponential, and your inside function is x. Similarly, if we're talking about a trig function, like doing trig, technically speaking, the sine function is the outside function and the x on the inside is your inside function. So that when we're also doing taking the derivative of trig functions is actually a technical chain rule type deal. But there's also, so similarly, like with an exponential, when you take the derivative of a trig function, they have their own special rule on top of the fact that it's also a chain rule. So like how if I took the derivative of an exponential, the rule for an exponential is that you keep the original the same, like you keep the original exponential the same, and then you multiply by the derivative of the inside function. The trig rules go as there's like this cyclic nature where if you take the derivative of sine, it goes to cosine, cosine goes to negative sine goes to negative cosine, then negative cosine goes back to sine, or yeah. And then it starts all over again. And then there's these rules right here when dealing with secants and tangents. So let's look at chain rule, a few examples of chain rule real quick. If I have a function f of x is equal to x plus 6. Now let's say 2x plus 6 squared. When I take the derivative of this function, looking at chain rule, I take the exponent, bring it down in front and subtract by 1. So I have this is equal to 2 times 2x plus 6 raised to the 1. Now I multiply by the derivative of the inside function. My inside function here is 2x plus 6. So if I take the derivative of 2x plus 6, I'm just given x or 2. No, yeah, I'm just given 2 because I just have one x here. So boom. So now I have 4 times 4x plus 6. That's like the most typical version of chain rule, using just an inside function raised to an exponent. If I'm doing something more complicated, like f of x is equal to cosine squared of x of 2, or actually, hold up. Yeah, let's do that. Cosine squared of x. So this, I always like this example because there's actually 2 ways that we can do it, employing different methods of differentiation. So I'll let you think about which method I'm going to do first. We can actually use 2 different methods here. So at first, why don't we do the chain rule? So as I've mentioned before, a trig function is technically an outside function with an inside function. So when we take the derivative of it, we can employ chain rule exactly how it employs. Firstly, I'll bring the 2 down in front. Boom. 2 cosine. And then this goes to 1, and then I'm multiplying by the derivative of the inside function, which the derivative of x is equal to 1. So this actually just becomes 2 cosine of x. All right, well, not quite done. This is 2 cosine of x times So actually, I said that kind of wrong. The outside function, because this is raised to a 2, is actually the fact that it's raised to an exponent. So it's this 2 power, and the inside function now is this cosine of x. So when I bring the 2 down in front, I went through this stage of the chain rule. Now I have to multiply by the inside function, which is cosine of x. The derivative of cosine of x is equal to negative sine x. So now my answer is actually negative 2 sine of x cosine of x. All right. Now let's double check this by doing it the other way that I've hinted at doing. So we can actually rewrite this function instead of cosine squared of x. We could just write this as cosine of x times cosine of x, right? If we do that, now we can recognize that these are 2 functions of x multiplied by each other, similar to how we do with the product rule. So now that I have 2 functions of x multiplied by each other, I can employ the product rule to take the derivative. So f prime here. If I take the derivative of the first thing, I get negative sine x times cosine x plus, I'll leave the first thing the same, so plus cosine x. And then as you can see where I'm going, this is cosine x times a negative sine x. As you can see, both terms are actually the same, being negative sine of x cosine of x, so that when you combine them together, you get negative 2 sine of x cosine of x, which is exactly what we have over here. So just a fun example of how you could take the derivative of a function of x 2 different ways, employing 2 different techniques for integrals. All right, now integration. I always like to make this specification. An integral is this thing right here. When you take an integral, you do the act of anti-differentiation. So this thing right here is not called an antiderivative. This is called an integral. It's just when you evaluate an integral, it's the act of doing an antiderivative. Or I'd say that because it's like, this thing represents so many other things. It doesn't just represent like the antiderivative. It represents like the area under the curve and center of mass and all these other, like, you know, moment of inertia, all these other things that you can do with it. And it also represents an infinite sum. So even if when you did evaluate it, you didn't even have to evaluate it like an antiderivative. You can just do like an infinite summation, but that's much harder to do than just an antiderivative. So evaluating an integral is much simpler to understand once you're very comfortable doing all of the derivative techniques. Basically, it's the act of just understanding what the function is and then what type of technique you would have to do, and then employing the opposite of that technique. So, for instance, right here, we have to do something called substitution because we have a function of x raised to a power. So it's just easier to substitute the function of x like this. However, I just want to focus on this part here. So if we're right here and we're taking the antiderivative, unlike a derivative where I would bring this exponent down in front and subtract it by 1, I'm going to instead increase it by 1 and then divide by that exponent. So instead of multiplying it and then subtracting by 1, I'm going to add by 1 and then divide by it. So add 1 to the exponent. So now I have u to the 3 instead of u to the 2, and then I divide by divide by 3 to get that. We do that because if you hypothetically were to take the derivative of this function you would bring the 3 down in front, which would cancel out with this 1/3. So because you'd have 3/3, which would just be 1. And then you would have 3 minus 1, which would give you 2, which would give you this original thing right here. When you're doing in something called an indefinite integral, that's when you don't have endpoints here. Indefinite integrals always have to be added with some generic constancy. This example, we have to use substitution to make it easier. Actually most techniques in integral integration end up being some type of substitution, like right down here is a trig substitution. It's just whenever you can make a substitution for a function to make the evaluation easier, then go ahead and do it. I think that should just be the rule of thumb. So right here, we can just say, let u equal x plus 1. And then, so now this thing right here is equal to u, but we have to replace everything within this integral or else it won't make sense. So we also have to replace dx. Dx is the derivative of x. So if I'm replacing things by u, then I have to figure out what du is. Du of this thing, if I took the derivative of it, would just be dx, because this is just 1, and then this becomes just dx. If I'm doing a trig substitution, trig substitutions require knowing some trig identity that makes it easier to simplify. So right here, when I have 1 minus x squared, I think back to all the trig knowledge that I'm sure you remember, and realize that 1 minus x squared is very similar to either the secant tangent identity or the sine cosine identity, which we obviously, you can see we use the sine cosine identity. So where you use the identity where sine squared plus cosine squared is equal to 1. If I rearrange that, I can say that 1 minus cosine squared or 1 minus sine squared is equal to the other thing. So here I'll say that let 1 minus x squared, or let x equal sine. So I can say 1 minus sine squared is underneath the radical. And if I have 1 minus sine squared underneath the radical, then I can replace this thing with cosine squared. Right here, recall that when we're doing a substitution, we have to replace everything. So we're also replacing this dx term. So if I say let x equal sine of u, then dx is the derivative of sine of u, which is cosine of u, du. So that's where this extra cosine of u comes from. Now you have cosine of squared in the radical, so that turns into cosine, and now I have cosine times cosine of u, so now I have cosine squared of u du. And this thing right here is much easier to take the integration of than this thing right here. Hopefully this is kind of bringing back some memories and is starting to, fire off some lights in your head. These methods are very important and are worth getting used to and memorizing and practicing. Right here is the most common methods for integrals and certain integration techniques that you would need to know and you should know easily. Emphasis on should know easily. So if you ever see something like this is just the same thing as the integral is 1 over x. If you ever see the integral of 1 over x, you should immediately know that this is log of x. That's something that they might have explained through a proof, but more likely they just defined that for you, and this definition is something that you just need to know. Similarly, with all of the cyclic nature of taking the derivative of a trig function, knowing the integral of a trig function or the antiderivative is important too. So Yeah. Remembering these is also just as easy as just remembering the derivative of each thing and just being able to go backwards. So if I know that the derivative of sine is cosine, then I know the integral of cosine is sine. You feel me? Similarly, that goes the same. That can be said the same for these. If I know that the derivative of tangent x is secant squared x, then I know the integral of secant squared x is equal to tangent x. Down here are less used, but equally important and will come up just as often, which is sad because I definitely don't memorize these as well as the other ones. But right here, 1 over 1 plus x squared is the same thing as like the derivative of like an arctangent, or similarly 1 over 1, the square root of 1 minus x squared is like your derivative of your arcsine. These will come up, and it's important to know what they are because you more often than not have to do some type of substitution to solve this, or get it in a way to where you can put it in this format. Like you might have a complicated function, and if you could get it into this type of format where you have 1 over 1 plus something squared, then you can evaluate it saying that this is arctangent of that something squared. You know what I mean? So knowing these definitions is also important, because if you could find a way to put your function in a form that looks like one of these, then you can just quickly evaluate it without having to do much actual calculation type stuff. And right over here is a quick reminder of how to take a definite integral. So a definite integral is an integral that has a particular bound that it wants you to evaluate on. So as I mentioned, the integral is the area between the curve, area under the curve. So this is a curve. This is the area under it in the yellow. If we're asked to find the area under the curve between -2 and 2, that's the same thing as taking the integral between -2 and 2, or a definite integral between -2 and 2. This is our function f of x is equal to x cubed. So I'm taking the integral of, I'm taking the integral from -2 to 2 of x cubed dx. If I take this integral using the integration techniques, I know that this is going to be x to the 4th over 4. Taking a definite integral just means that you have x to the 4th over 4 between -2 and 2, right here, -2 and 2. And then you evaluate this by first plugging in the top value into the function and then subtracting it by the bottom value into the function. So the way this looks like, it looks like 2 to the 4 over 4 minus, and in here is -2 to the 4 over 4. This obviously just gives us, since this is even, this gives us the same value. So I get 4 minus 4, which is equal to 0. However, if we're trying to find the total area, like the max area or just the magnitude, then we don't really want to do a full integral, because that'll assign a negative value to this and a positive value to this. Where if we're just trying to find total area, it doesn't matter whether it's negative or positive. So instead, we'll split the graph up into 2 separate integrals to get a total area. If we do that, then you're doing the definite integral from -2 to 0 and from 0 to 2. If you do that, then you'll have 4 on one of them and -4 on the other. Therefore, the area for both of these segments is 4. And then if we add them together, then your total area for the underneath the graph is equal to 8 units. So hopefully this was a helpful reminder of some differentiation and integration techniques. There are many more integration techniques that you learn going forward into Calculus 2 as well. But these are the most used and widely understood. So especially when you're going into these harder classes and having more complicated functions, they would expect you to understand all of these right here, so that part of the solution is getting it into a form that you can do one of the methods that you already know. And that wraps up our calculus review.